All right, thanks everyone for staying to very nearly the end. I'm going to be talking about IPVM and, in fact, how all these projects can be better together. I'm going to be talking about something slightly different from what we've been seeing today, which is more about standards governance and a community process, right? Things that have, instead of a MIT or GPL license, that have a intellectual property release, right? That are more pros and specs than code. The code for IPVM, the reference implementation, will be talked about tomorrow by my colleague Zishan, and that's the talk about Homestar. Joe Armstrong, I should say the late great Joe Armstrong of Erlang fame, had this wacky idea that what if not only every machine could be networked, but every process on those machines across the world. This isn't really the seed of the idea for IPVM, but it's the sort of thing that we hope to enable, right? To make it so that you can just call into any particular process and have it be automatically done. To talk about this utopian vision, this is me, I'm Brooklyn Zelenka. You can find me anywhere on the internet as Xpeed. I'm the co-founder and CTO of a company called Fission. And for the past several months, I've been acting as the IPVM spec wrangler, mainly hosting community calls and just getting people generally involved, which is to say that this is less a talk about things that are specific to Fission and more the IPVM Working Group sort of broadly, which is, Fission's involved, but it's also has really major contributions from Bakal Yao and Daghouse, so the people behind Web3 storage as well as some contributions from Ceramic, Warpforge, and a bunch of individuals too. First question people usually have about IPVM is, how is it different from the FVM? So Filecoin and IPFS obviously both do storage and transmission of data, but in a very different way, right? One of them has blockchain and consensus, and the other is much more focused on distributed systems and content addressing and locality. Filecoin has the FVM, and IPFS will have IPVM. And the hope is that we'll be able to complete this diagram so that all of these things work together in the end. We're building that from ground up. What we're talking about, in general, is nothing less than connecting every device on the planet, all services and all users, in a way that literally nobody can stop us, right? We can wrap any service and have it talk this common format. I sometimes like to talk about this like it's equivalent to HTTP or TCP, but instead of for data transfer, for compute, in the same way that IPFS and content addressing get you open, interoperable, and everywhere IDs and data transfer, we can have this for computation as well. And whatever we build has to be substantially better than the status quo. We can't say, it's a slightly worse AWS Lambda, please use it, right? It has to actually have real benefits to people, which is good, because I think the time for a lot of these ideas has finally come. I think we do a lot better than the status quo. The web today is really designed for a world where you had a beige box under your desk, and you could point at it and say, the database lives there. Or point at a certain place in a server rack and say, my application lives here. We don't live in that world anymore. We invented LAMP in the 90s and have been trying to extend that metaphor since. And this has led to essentially the entire world that we have today with computation. It's very server-centric. We have deep specialties, front-end, back-end, DevOps, Docker, Kubernetes, all of these things. It's really difficult to train engineers to do all of this, let alone to actually maintain such a system. The level of complexity has become very, very high in trying to extend this metaphor ad nauseum. The other thing that this has produced is a centralization of who runs the data centers, right? AWS, so Amazon, Microsoft, and Google run approximately 2/3 of all of the cloud infrastructure today. And that's a perfectly rational, fine thing to do in a world where you have the database. It totally makes sense that you need a large data center, and a handful of them around the planet. But if we don't want the picture over time to be these providers to continue to eat up more and more of the space, we need to do something slightly differently, right? We want to take the light cone of the future, all the possibilities inside of that, and say, instead of just barreling down the middle of this, What if we tried doing things slightly differently, not so that Amazon, not only so that Amazon doesn't own the entire future, but so that they can also participate on an equal playing field? One of the consequences of having a certain number of data centers is if I want to send a message from, we'll just call it, center of the continent, from Winnipeg to Saskatoon, it is, in a good case, going to go all the way through US West and then back, which is, if I'm sending a text message, not really a big problem, but in aggregate, that is a lot of time, energy, carbon, and just physical infrastructure that we have to maintain. When we zoom out to the world, here's where all of, and I'm going to pick on Amazon a little bit because they're the biggest one. Here's where all of Amazon's data centers are. And this is roughly the geographic distribution, right? So there's quite a few in North America and Europe and Asia. And this is a perfectly rational thing to have in this world, right? Where data lives in a particular place. You're going to put it where you make the most profit, which is not in places like this or like this, where people are coming online at actually a very high rate, and that have very high populations. Right? Even just in this one circle, there's 50 million people. To put that in, by comparison, in North America, we've got to have about 50 million people per data center. In South America, we have about 7 times as many. And in Africa, there's about 1.5 billion people for that one data center at the bottom there, which is actually more expensive to store data on and to do compute with than US East. Because there's less existing infrastructure, compute infrastructure, fewer data centers, and fewer people actually using it, so it's more expensive to run. We've heard a lot about data gravity today. We literally can't consume and handle this raw volume of data coming off of IoT, geospatial data, large language models, and things like Filecoin, and literally compute over data. The stuff that we're all talking about doing today, taking petabytes of data, computing over it, and dumping that data back into a system, and have it live in only a handful of places. We have to do geographic replication if we want to have high availability, right? That's literally not something that we have a choice about. We have to make copies of data, but we can't keep up at the existing rate, right? We have to send things around. We have to keep as much as we can off the network and compute on them locally and send results in aggregate. So Tesla collects geospatial information as you drive your car around. They do learning on device, which is to say in the car, and then send little snapshots of the data back to a data center. We can do a lot more, a lot closer to the user. Chris Micklejohn has this wonderful paper, A Certain Tendency of the Database Community, that says that the current situation is literally untenable, right? We have to embrace a design that brings things closer to device, closer to the user, that doesn't say the database lives there, it's wherever the data is being produced. We can't have a small number of sites where data is consumed, stored, and operated on. Which is to say, I think uncontroversially for this room, that places aren't the way. We want things that are content addressed, that can move around transparently, and that can be stored in multiple places, or even where they're produced and consumed directly. The good news is that we have finally some signs of a way out of this, the current world, out of the status quo. When the web was started, it had these 5 principles, right? And a lot of those actually sound a lot like Web3 principles, right? Decentralization and consensus in this case mean slightly different things from what we'd think about from Web3 focus, right? Decentralization, the web or the internet was designed to be resistant to nuclear attack, right? So you actually want to spread things out. But you have a bunch of different entities, people, companies contributing hardware to the network that all work together. So we've actually done a really great job of decentralizing the media layers of the internet and of the web. And now we need to do the hard work of getting through the last, the second half, basically. Unlike the 90s, where everything lived in a certain place and you had the one server where it lived, and maybe you had a desktop that you could dial into it from. Now we have this very heterogeneous view of different devices, different locations, different distances to the user as well, where I can call from a browser into a WebAssembly module, into the cloud, or into an edge pop, or into a Commons network, and call into Ethereum or IPFS. And we need to be able to have this stuff move around and work automatically and transparently, right? This is a much less ordered picture than client-server. So when we started working on compute a few years ago, we knew we wanted to do location-independent compute, which means you need location-independent data. But if you want to do that in production, in a real-world scenario, you actually first need to solve for location-independent auth. Most people, and we're going to take a little digression into auth here, most people are familiar with access control lists, ACLs, where you have a user, and they want to access some service, and they send a request, and that gets stopped by a process that says, hey, who are you? Show me your ID. Are you on the list? OK, great. You're on here. You're allowed to do the thing that you're asking for, and then they'll pass it on to that service. And in some ways, this is very convenient. You can put this process in front of really anything. The downside is that the user and the process aren't in control anymore. They don't have a direct relationship to each other. The thing in control of who's allowed to access what is this process. And its list sits in a particular place. We can't synchronize it worldwide. You're always behind. So what people do is they put that in a central place, and you're always calling out into it. So you always have to make this request, which means it doesn't run locally. It doesn't run offline. And scaling this up, as Google has discovered, is actually extremely painful. And even they move to something that looks more like capabilities, which we'll talk about right here. So capabilities model slightly different. We have a user and a process, and they know where to find the process, and they can send it a cryptographic proof that they're allowed to access it. And there's nothing else. They're the ones in control. It's stateless. All the information that they need to do this is contained in the request itself. So instead of it being like a bouncer, it's now like having a ticket to a movie. I can take that, and they don't have to check my ID. They're just like, do you have the ticket? Yes or no? Great. Theater 3. I can make copies of it and hand them out to other people. I can hand them off to other people that I'm collaborating with. So if I can't make it to the movie, I can hand Zishan a ticket, and he can go in my place. And this isn't only more flexible. This is easier for people to reason about. So this is a typical OAuth flow. Asking if the application asking the user, hey, can I have access to this thing, takes 6 steps, including a third party, this authorization server. And then when the application wants to actually go and use it, there's 4 steps. This is quite a lot of back and forth. The spec is quite extensive. And you have this extra stage in the middle, this authorization server, that we would prefer not to deal with. And so with a capability-based model, something like UCAN or ZCAP-LD or any of these systems, this radically simplifies it by removing this process in the middle, and to color code it to be the same, it can look like this. This gives us the ability to do disorderly programming, where we don't have to have these perfect, pristine APIs for everything, where we can just pass around authority, and the network topology, the direction and the layout of the requests is the flow of authority. You don't have to go into a single central source, that when it goes down, the whole network goes down. Fundamentally, developers don't want to have to think about how authority works and how their invocations are going to be handled. What we were promised with serverless was that you would just have this underlying compute substrate that you'd be able to throw work at and have it compute. And we never really got that. What we actually want is to make requests and to get responses, and to not have to conform to really specific, rigid APIs that are different between Amazon and Azure. Right? We just want to be able to say, hey, whoever has capacity, please run this for me. So let's talk about a compute substrate. things are becoming increasingly clear that WebAssembly is eating the world, slowly but surely. And as more of these pieces come together, so the WebAssembly component model, for example, and more tooling, this becomes a more and more obvious choice. Now, that's not to say that IPVM is only about WebAssembly. It can, in principle, connect to anything. In fact, we're very directly going to be working with things that aren't WASM, but WASM has three major advantages. You can write it in any language you want. It runs literally everywhere. It'll run in a browser, on a server, on a phone. Doesn't matter. And you can put it into a deterministic mode. So that if I run something today, or a year from now, or you run it, with the same inputs, we'll get the same outputs. So I said before, auth, data, and compute. And we want these things to run everywhere with location independence. We now have this full stack. You have capabilities at the bottom. You have data being moved around with content addressing, something like IPFS, or if you want it to be permissioned access to data, so you have a regulatory requirement or it's private data that you don't want everybody to have access to, you can use something like the web native file system. And above that, you have WebAssembly. And all three of them together, combined, form the building blocks of IPVM. There's this old idea going back to the 50s called code as data. Computation, obviously, is we're going to take some arguments and apply them to a function. But that function is also content addressable, right? It's also some data that sits on a disk. We can roll this up into a task and also attach to that a little bit of information about scheduling, configuration, et cetera. And this is a little bit like having a closure, having an anonymous function, right? Where we're not saying run this thing right now. I'm saying here's a description of what I would like to have run at some point in the future. And I can give you a handle to it. That's just the name of this variable, in this case, message. And passing that around doesn't do anything until I actually say, hey, run this. And I put the parentheses on it, and it actually executes. We'll see in a couple slides when we look at the schema exactly how that's done. But the short version is you actually have to sign to say, hey, I want this thing run. Actually go and do this for me now. When it executes and you get back a result, you have a receipt that points at the original description of the task. So this is content addressed compute. You get back pure values and effects. So pure values, if you do 1 + 1, you'll get back 2. And effects are things that you want to on-queue to happen next. So this could be send an email or do another pure computation or anything else, right? Something that is going to need to take resources off the network. And then some metadata, trace information, success or failure, tags, anything like that. Instead of content addressing, this is input addressing. So content addressing, we have some data, and you hash it and use that as the key value. So the hash is the key, and then the value is the value. Input addressing, you get a receipt as the value in this pair. But the input is the hash of the we call it an instruction in IPVM, but the description of what you want to have run. So not the scheduling information, literally the information about, I want you to run these arguments over this with this function. Hash that together, and you'll get a receipt. So we can still stick this inside the same DHT. We can still stick this inside of Kademlia. The difference is, instead of validating with a hash, you validate it with either trusting the receipt. You can, in fact, have several receipts and check them together. So we actually have fully deterministic verification. And or you can run it yourself and double check the value. Here's the actual schema. So an instruction is a resource by its URI. The operation you want to run on it, so it might be, with this Docker container, run the container with these inputs, and then a nonce to make them unique. A task attaches to that some metadata and the authority, the UCANs, you need to actually run this thing. Around that, we have an invocation, which is a signature, and any other information that you need to prove about it. So the reason this is broken out into this thing called authorization is because you might want to sign over a whole bunch of them at the same time. Like this, so there's a whole bunch, and those might you often want to connect together into a workflow. You don't want to make one request and then wait around. And when it finishes, make the next request. You, in fact, want to be able to run entire graphs of computation and request that all at once. Because this is the merger of IPFS and WebAssembly, we want to use as an interface IPLD. But WebAssembly doesn't take IPLD, right? It takes WebAssembly interface types at best. I mean, strictly speaking, it only takes integers or numbers and linear memory. But the WebAssembly, the Bytecode Alliance has produced the spec on top of it as part of the WebAssembly component model, and are building tooling out to make all of this work. So IPVM will work out of the box. Somebody writing a job, running a task, can use regular off-the-shelf WebAssembly tooling. Normal, nothing else. The downside of this is these things are still very much a work in progress. The specs aren't formalized yet. We're told that they should be formalized by the end of the year and finalized. So we may end up doing a little bit of work to make things compatible while we're waiting for that to finish. And there's this impedance mismatch between these two. So IPLD has 2 numeric types. WIT, the WebAssembly interface type spec, has 10. Zishan's done a bunch of work to make these translate in both directions. So we can consume IPLD, convert that into WIT, run WebAssembly, and on the way back out, convert that back into IPLD. So you don't have to think about, unless you're writing the job, when you're actually invoking the thing, you don't have to worry about this at all anymore. So you can create reusable tasks that somebody can call with different arguments, and they just have to reason about it in JSON. This is what an actual document looks like, or the JSON layout of it. Being IPLD, it's encoding agnostic. Pretty straightforward for a workflow system. And because this is underlaid by capabilities, we can transfer the authority around and say, hey, I actually send off to a broker, hey, I want you to run all of these things. And it can break that apart and say, OK, well, this one can run this one task, and this other service can run this other task. And they can sub-delegate as well to say, well, I can only run some of these. And they can send to another one, say, well, I'm going to run the one here represented by a teddy bear or the champagne, but I can't do the rainbow. So I'm going to sub-delegate that to somebody else. Distributed invocation or promise pipelining. You often want to, as I mentioned a couple slides ago, define an entire graph of execution. So here we have a DNS update, and then we're going to email a couple of people that it was successful, and then after the emails are done, update a report over HTTP. And this expresses the intent, right? We're going to await each of these arguments, and it just feels like normal promise-based computing. But the distributed runtime can decide in advance the most efficient way to run these things with the required capabilities. And if you don't have a GPU, you can't run a CUDA job. So it'll look in the network who's able to run these, do the matchmaking, and then say, well, the most efficient way for us to do this is to actually have some network requests in the middle here. And it'll handle that automatically behind the scenes for the user. They don't have to worry about any of this extra complexity. It's all declarative. Because these things are input addressed, and at every step we're generating receipts, that means that if somebody later wants to reuse part of a computation, they can actually skip that step completely, consume the receipt, and use its value in its place. So we actually take load off the system. The more people that are using it, the more receipts we get, and the fewer computations you have to run relative to the number of jobs asked for. Of course, there's going to be a long tail on that, but it lets you remove different parts of the computation and have things automatically finish. You'll see tomorrow in Zishan's presentation, crashes are no longer a problem because you can pick up from where you left off. Or having 2 nodes trying to run variants of a job can now skip entire steps and do that variant much more quickly. I mentioned before that this is fully verifiable computation, so we don't even sample the results. We check their content addresses on the way out of the receipts and say, do they match? And if they don't, because this is, at least in the WASM case, they're fully deterministic. If they don't match, we actually run them on a trusted node and say, okay, well, this one's lying, so we can slash them. This is called optimistic compute. So we run a pipeline, but you actually run it in multiple machines in parallel, and then you can check. Okay, this one of these two is lying. We're going to run just the step that they disagree on, and slash them if that doesn't work out. Over time, we would actually like to move over to zero-knowledge proofs. They're a little bit on the slow side today for WebAssembly, but entirely doable. So it depends on how much performance versus verifiability you want using the, I think, oft-quoted at this conference, Wan's triangle. Something that we discovered quite recently that this gives you sort of for free out of the box is reverse lookup. So if you have a large language model, or any AI task, really, we have our input ID to a computed result, which gives us reverse lookup. We can say, for some bit of content, I want to run an AI classifier on it, for example, moderation. I don't have to run that every time. I can say, run this model over this data. Has anybody done that before? And get back a result instantly without having to run the entire thing. And you'll get back all the results, all signed, and you'll see the level of consensus on this answer. Same thing for cryptographic operations. So doing things with signatures can sometimes be very slow. You can actually roll these up into larger computations and just check the top signature and say, yeah, all of these have already been checked by 100 people. Usually when we're scaling up and we're adding parallelization, we want to get this linear growth so that if I have 5 machines, it'll be 5 times faster, and we'll be able to handle 5 times the load. That doesn't often happen. So there's Amdahl's law that says that because of coordination, this will actually level off. In practice, it's actually typically worse. So because you have incoherence, you're waiting around for data, you're you're getting bad data from somebody, all of these things, you actually get a drop-off. So there's an equilibrium point of like, this is the best you can do, even if you have infinite compute resources, it'll stop at some point. When you have receipts and you have a input addressed system, you actually get the opposite effect because you don't have to run the computation all the time. You can take load off the network and actually do better. This looks a lot like hotspot optimization or global adaptive optimization in something like Java, right? Where the more people are running things, the faster the compute can happen. And you can take a WebAssembly module and compile it down to even a faster version, as long as it's semantically equivalent, or even specialize it so that if you're always getting with certain arguments, you can run a specialized version of that runs even faster. And finally, and I think I can do this in 2 minutes, we'll talk briefly about safety. Something people worry about a lot is how do we make distributed computation safe in a trustless setting? It's a tall order. Microsoft and the Azure team have looked at this a fair bit. And one of the papers that we found very inspirational is called Ambrosia. And it essentially says if you can reduce things down to pure data, which is what we're doing with content address data, then you can take all of the learning from the past 50 years of database systems and apply them to your computation. You can get atomicity on arbitrary computation. It's called virtual resiliency. The approach we've taken, it has these 3 properties: determinism, idempotency, and mutability. And whether or not these are turned on or off for a particular computation gives you safety. So this is a simplification. It's more complex than queries and pure computation and mutations, but for argument's sake, you can interleave computation and queries, all that you like, as long as the mutation happens only at the end. And once you have this, you can have compare and swap atomicity. The downside is that you can't interleave mutation throughout. So you can do a huge number of things, you just can't do any computation in this model. We're going to enable a flag that's basically like unsafe true or -- force that says you know what? If it fails halfway through and you've got a bunch of interleaved mutations, you're going to have to clean it up. But by default, this is the safe mode. Simplified version, we have queries, we have computation, and these two can go back and forth as long as you end with mutation. And because we're not giving users the ability to define what happens, the order of execution, only that there's data dependencies between them, we can reorder computation so that mutations happen at the very end, even if it's not laid out at the very end. So that's safe. So to wrap up, this is all open protocols. And not only is it done in open source, these are open standards. Anyone can get involved. You can use any piece of this. You don't have to buy into the entire stack. We want to work with people, especially early on in the project, to make it work for all of your use cases. Drop us a line. Get involved. These are the specs to date. So we have UCAN for authority, IPLD WIT for the IPLD WIT ABI interaction, VARSIG, which we would have called multisig, but it's how to sign over multiple things and how to differentiate between different signature types in IPLD. UCAN invocation and UCAN pipelines, which you've heard about a fair bit today. IPVM tasks and IPVM workflows to get the entire graph. And the next piece that we're going to work on is channels for doing things, anything that's consumable. So fuel, money, tokens, timeouts, et cetera, saying, OK, I'm allowed to use this many network resources or this much economic resources. We can do that entirely off-chain, built on top of UCAN. Thank you. Yep.
Sorry. Hey, fantastic presentation. Love the approach. Could you share any perspectives over the next year, 2 years, 3 years, how you would like the use cases or demand for this technology to come about, where you'd like to see the use cases come from?
Yeah, absolutely. So this is generalized compute, right? So we don't want this to be a project on its own that runs its own compute network, right? We want Bacalhau to plug into this. In fact, Bacalhau's contributed significantly to the specs to date. To take, so we've thought about a whole bunch of them. Obviously, fissions, like my company's interest in this, is more on the WebAssembly side. So we can do things like anything that a web developer would want to use a serverless function for, right? Because it has this, the ability to run in the browser directly. We can take only the really expensive computation off of that, and everything else can run directly in the browser, right? So web developers is Fission's main use case. We've heard from other people like, hey, could you take blockchain, anybody that's built on top of WebAssembly, could you take their jobs and put those on the network? Because it's all verifiable and checked, you can essentially get a optimistic rollup for free. So you can take that off of, say, Cosmos, or we haven't talked to the Filecoin team about this, but like in concept, we could run Filecoin jobs as well. And then we want this slowly to have more and more task types. So I didn't really talk about the open world assumption that we have, despite it being in the title. I think Zishan's going to talk about it more tomorrow, where we want people to be able to, with a plugin system, drop a bunch of descriptions of jobs into a directory and have it be able to call out into Docker or into a Python script or things like this without having to recompile the binary and then do the automatic matchmaking in the system. So you can say like, hey, I can run a CUDA job and I need a CUDA job, and you don't have to wait for a spec to get written for that. It'll just automatically match those up.
Hi, Brooke. The first question is, how'd you get to be so cool? And great presentation. Second question is, I like the design of effectively, that's not the phrase you used, but let's say, global memoization of computation. So that actually leads me to a question, which is, if you're going to be going backwards through history and looking at signatures for who's computed what, what is the generalized process for routing who should be performing the tasks? And also, how do you determine against, like in a scenario where, like, 5 years ago, Juliana and I decided to troll the whole network by both signing off on 2 + 2 = 5, right? And then later on, if sometime far in the future somebody looks up and sees, oh, okay, well, you know what, multiple people signed off on this. Like, how does that step go into the verifying, that, like, being reasonably sure that somebody's not poisoning the memoization table of basically all computation?
Yeah, absolutely. It's a great question. So I'll handle those in reverse order. How do you guarantee that nobody's poisoning the table? So in optimistic verification, you lock up capital, right, in some escrow. And if you're later found to be lying, you get slashed, and that gets taken from you. So it's not handled at the computational layer in the way that a zero-knowledge proof would handle that for you, where you literally can't lie. It's so unlikely that you'd be able to produce a cryptographic proof of the false thing that it doesn't matter. This relies on having everyone be truthful, because there's so much money at stake for them to not lie about it. And so there are a number of these systems in practice today. The major problem with them is if there's a very high value target, so you want to fool somebody into making a multi-million-dollar investment, let's say, then you probably want a large number of confirmations on that data, and that's a tunable parameter. But you can, it's not perfect, right? The higher replication factor you get, the better the likelihood that that's going to be a correct result, because it's less likely that those are all going to agree. And you have to run, in the case of a disagreement, you have to run on a trusted, network-trusted node, right, for that step. So there are absolutely trade-offs on that. This is the performance versus verifiability scale. The first question was, how do you know who to route to, I believe, was the second one? So we have a concept of affinities. So verifiable deterministic WASM can run literally anywhere. So that's going to be highly available and picked based on latency and reported availability of resources, right? So if you have somebody sitting next to you and you have a Bluetooth connection with them, it should send it to them, right? Or if you have your computer at home that you trust because you've set that up in your capability, it'll send it to your idle compute resources at home. If you have something that requires more like a GPU or specialized hardware or knows how to run a kind of job that not any node in the system knows how to use, then we start using affinities and checking who's actually able to run this, who has a high reputation score, or we're going to send it to you because we're more likely to get a good result from you. The other one that's interesting with data gravity is saying, who has this petabyte of data? Because I should send that to you rather than transferring that around to somebody who has the compute. Great, thank you.